Let's take a few minutes to explore Riemann sums. Riemann was a German mathematician who did a lot of great work in mathematics, and he is credited in calculus with the idea of using rectangles to collect area when you're given some data or if you're given a curve. And you did something similar with your driving project this summer, but rather than using rectangles this summer, you used trapezoids. So we're just going to extend that idea of trapezoids to rectangles. Let's use as an example this calculus problem from the AP exam in 1999. And as you'll notice here, it's a problem about water flowing through a pipe, and you're given data. Every 3 hours over the course of the day, you're given in gallons per hour the water flow. And you're asked in part A of this problem to use a midpoint Riemann sum with 4 subdivisions of equal length to approximate this integral. And you'll recall that that integral is simply the area under this data, or if the data were part of a smooth curve, that would be the area under the curve. And because we're using 4 subdivisions of equal length, we're going to break our 24 hours into 4 6-hour increments. And those increments will go from 0 to 6, from 6 to 12, from 12 to 18, and from 18 to 24. Now, let's see if we can visualize our rectangles. And you don't actually have to draw these when you're working a problem, but for the sake of visualizing, I want to have you see these rectangles. So I have my axes, and I'm going to put along the x-axis our increments in 6-hour intervals, and those are measured in hours. And then along the y-axis, since our data go up to about 11.5, maybe I'll do increments of 5. And those are measured in gallons per hour. Alright, now I'm going to plot a few points. I'm not going to plot them all, but just enough so that we can get an image of these rectangles. So our first point is 0, 9.6. Our next point is 3, 10.4. And our next point is 6, 10.8. And I'm exaggerating the change in y there just so it's easier for us to see our rectangles. And then let's continue on. At 9 we have a y value of 11.2. And then at 12 we have a y value of 11.4. So there are our points. And now we're going to see if we can build our rectangles. Now our first rectangle is going to have a base of 6. And we have 3 choices for the height. If we were doing a left-hand Riemann rectangle, we would go up to that first data point. If we were going to do a right-hand Riemann rectangle, we'd go over to the end or the right edge of our interval and go up and choose that y value as our height. But we're doing a midpoint rectangle, so we're going to go right between the 6, 0, and 6, which is 3, and use that y value. So the y value we're going to be using here is the y value 10.4. So I'm going to draw that rectangle now. It'll go right across here, and it'll go down along its edges like that. For our next rectangle, we're going to choose, since we're doing a midpoint sum, the y value at 9. And the y value at 9 up here is 11.2. So I'm going to go ahead and draw that rectangle. And in a similar fashion, we would do all our rectangles that way, the other 2, to get us through to our 24 hours. Alright, now let's see if we can calculate those areas. Our first rectangle has a base of 6, a height of 10.4, so our first rectangle will be 6 times 10.4. Our next rectangle, again, has a base of 6, and a height of, this time, 11.2, so 6 times 11.2. In similar fashion, our third rectangle will have a base of 6, and its height will be the height at time 15, which is 11.3. And then our final rectangle has a base of 6 and a height of 10.2. And you could calculate that total, and that total will be the area captured under this set of data. And if you look at the units, we have gallons per hour and we have hours. When we collect area in here, we are multiplying gallons per hour times hours. And we're going to be getting as our answer then, in units, gallons. So here's a summary of what we did. We just calculated a midpoint Riemann sum, and what I want you to notice here is that we used as our y values in this example 10.4, 11.2, 11.3, and 10.2 because we were asked for a midpoint sum. Now had we instead been asked for a left-hand Riemann sum, we would have used the y value on the left-hand edge of each interval. So, for example, in the interval from 0 to 6, we would have used the y value at time 0, which is 9.6, to build our rectangle. So, those y values for a left-hand sum would be 9.6, 10.8, 11.4, and 10.7. In similar fashion, had we been asked to do a right-hand Riemann sum, we would have used the right-hand y value in each interval. So in the interval 0 to 6, we would have used the y value 10.8. So those y values that would build a Riemann sum from the right would be 10.8, 11.4, 10.7, and 9.6. One more thing I want you to notice. In our example today, each of the rectangles had the same base of 6. That won't always be the case. Sometimes you'll be presented with data where these increments are not evenly spaced, and as a result, these bases will be different. If they're the same, then you can do one nice thing, which is factor out that 6, since each base is 6, and then you simply have to add the y values that you're working with, and then multiply the result by 6 that's been factored out. But if these increments are not evenly distributed, then you won't be able to do this factoring out, and you'll have to work with each base separately. That's it. I hope Riemann sums make a lot of sense.